Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I wanted to do a post-quiz walkthrough. So this is going to be the post-quiz review for the quiz, which is covering our topics on electricity and magnetism. So this is the electricity and magnetism quiz. And this is the quiz which is corresponding to Chapter 8 from our physical science text. So let's go ahead and see how well we did on this quiz. Alright, here's the item analysis for the quiz on electricity and magnetism. And it looks like we are still finishing it in a reasonable amount of time. That's good. Remember, you have a 90-minute timer to do these quizzes. It looks like on average people are taking about 55 minutes. So it looks like you all have plenty of time to do the quiz in. The average score was a little lower on this one than what it's been on the previous quizzes. So I suppose if we judge solely by this average score, this is maybe the least easy quiz that you've had so far. And Blackboard sort of concurs with that analysis as far as how the questions break down. I guess there's only one really easy question and 11 that are only in the moderately easy range, and then 8 more that are only not as easy as the others, that are almost uneasy. And so it says that there's basically 8 hard questions. I see that a few questions had 0 people get the answers right. What I think I'll do in this quiz walkthrough is I'm going to look at a couple of the questions that everybody who attempted this quiz did. So 27 attempts means everybody attempted it. So the 2 that everybody attempted and did the worst on is this one that only about 26% of you got right, and then this one that just under 50% of you got right. And I will also maybe look at a couple of these that a handful of you attempted and nobody got right. So that's how I think I'm going to proceed with today's quiz. Okay, so I suppose that, for lack of a better word, the easiest of these 4 least easy questions would be this one that's a multiple answer question. It's labeled MC14. That of course means that I pulled it from your homework. It was multiple choice question number 14 on your homework. And the question in your quiz is this, and of course on the homework the original options were basically that this was option A, this is option B, C, D, and of course in the homework this was not one of the options. So I'm going to go ahead and just eliminate that one right now. So how could you get this question right? Well, one way of course is that you could flip open your book to page A24. That's the page that says answers to selected questions. Look down to chapter number 8, look at answers to multiple choice questions, look up question 14 and notice that it says the answer is B. So that's how you could ensure getting this question right. But you probably also might want to know, why is the answer B? Okay, well, let's go ahead and take a look at our notes to find out. So let's flip through the actual notes that you have for this course, and if all you did was look at the notes, then it may be a little difficult to answer this question, I suppose. This one is the slide that you have, which is for a step-up transformer, and you can see a little diagram that shows the primary coil with fewer windings and the secondary coil with many windings. And the statement is, since the secondary coil has more windings, the induced AC voltage is greater than the input voltage. And then it says the factor of voltage step up depends on the ratio of windings on the two coils. So this one is basically saying if there's more coils on the secondary, more windings on the secondary coil than on the primary, you're going to be stepping up the voltage. And that's about as far as the notes themselves go. Of course, if you also read the textbook, you would find that it says that, and here I'm actually reading from the section in your text, section 8.5, the part under transformers. It says, because the secondary coil has more windings than the primary coil, the induced AC voltage is greater than the input voltage, and this type of transformer is called a step-up transformer. However, when the voltage is stepped up, the secondary current is stepped down. Okay, so this tells us that if the voltage output increases, then the current output must decrease. And if we just left it there, then maybe you would, by assumption, by implicit reasoning, say, okay, well, could it work in the other way? If we had more windings on the primary coil than on the secondary coil, would that therefore step down the voltage and hence step up the current? And the answer is yes. Let me turn the page in my textbook, one more page. Basically, it tells you why you step up the voltage. It's basically so that you have a lower I squared R loss. By stepping up the voltage, you step down the current, and therefore the I squared R loss decreases. And then it continues on the next paragraph. Of course, such high voltages cannot be used in our homes, which in general have 220 to 240 voltage service entries. Therefore, to get the voltage back down and the current back up, a step-down transformer is used, which steps down the voltage and steps up the current. This is done by simply reversing the input and output coils. So if you had reasoned that way, then you would in fact be correct. That means if you have more windings on the input than on the output, then the result will be that the voltage is stepped down and the current is stepped up. You could also have attempted to reason through this in a more quantitative manner by looking at the equation 8.10 in your text, which is on page 228 of my 14th edition textbook. It's the same page, the second of the two pages that I was reading from. The first, of course, was 227. Or you could look in the notes and find that same equation that says V2 equals N2 over N1 times V1, where V2 is the secondary voltage, V1 is the primary voltage, N2 is the number of windings in the secondary coil, N1 is the number of windings in the primary coil. So this suggests to me that if the secondary coil has fewer windings than the primary coil, then this ratio must be less than 1, and so my secondary voltage must be less than my primary voltage. And in fact, on the next slide in the notes, an explicit example is worked for a step-down transformer in which we do that. So we have more windings on the primary than on the secondary, and so the voltage on the primary is lower than the voltage on the secondary coil. Okay, so this one basically says a transformer has more windings on the primary coil than on the secondary coil. This is basically saying that N1 is greater than N2. Okay, so since V2 is going to be N2 over N1 times V1, this is implying that V2 must be less than V1. And by further implication, also that I2 must be greater than I1. Because remember, when you step down the voltage, you step up the current and vice versa. That's just simply a conservation of energy thing. So this is conservation of energy. And this is because we're basically saying that the power in must match the power out, and power in this case is I times V. It's the Ohm's Law power. So if P in is equal to P out, this implies P in over P out must be equal to 1. And so I1 V1 over I2 V2 must equal 1. And therefore, if I step down V2, I2 must go up to make up for it. So this and this are equal. And so that means that we are stepping up the current. That's why this is the correct answer. You might also be asking, why is it that this actually steps up the voltage? And that's sort of explained a bit in your text, again on pages 227 through 228. The basic reason is that you get a magnetic field that is going through the primary coil and through the secondary coil, and you are basically able to induce current from the primary into the secondary coil via the same general effect that we are discussing in this whole section 8.5, which is magnetic induction of a electric field, and therefore of an electric current. So this is basically an application of electromagnetic induction, if you will. Okay, the next least easy question on this test was this one that was marked EX03. That means that it is example number, or exercise number 3 from your homework. And it basically asks us, what is the magnitude of the Coulomb force between a charge of 0.6 coulombs positive, which is 3 meters, separated from a second charge of 0.2 coulombs negative, and assuming that there are no other charges that can affect the force between these two. And then specifically it says that if it's a positive answer, then this should mean that we have a repulsive force, and if it is a negative answer, it should be an attractive force. I will throw out here that this is a slightly modified version of the problem in your text, because in your text this right here was also positive 0.20 coulombs. So of course this means that you should switch the sign on your charge. With that said, let's go ahead and see how to do this question. The key equation to use, or the key principle to use in this problem, is Coulombs Law. And so Coulombs Law says that force, the electric force between two charged particles, should be equal to the Coulomb constant times the charge of the first times the charge of the second divided by the distance between them squared, where the Coulomb's constant is 9 times 10 to the 9 Newton meters squared per Coulomb squared. This, incidentally, was also the subject of actually the first two examples in this set of notes. So you can also go back and review those two examples if you want more on this problem, but I'll go ahead and work this problem with the actual numbers given. All right, what we have is that the force should be K times Q1 times Q2 over R squared. So let's go ahead and draw that just for fun. So here's the positive charge. This was 0.6 coulombs, it's going to be separated by a distance of 3.0 meters from a negative charge of minus 0.20 coulombs. This was 0.60 coulombs. All right, and then, of course, the Coulomb constant, K, was given on that slide as approximately 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. Okay, so let's go ahead and plug everything in and see what we get. So this says that the force should be 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. That needs to be multiplied by plus 0.6 coulombs, and that is times minus 0.20 coulombs, and then we divide everything by this 3.0 meters quantity squared. Okay, so this guy right here is basically going to be equal to, okay, let's do the 3 squared thing. So this is actually 9.0 square meters. And so I notice that I have a 9 and I have a 9. So I'm going to go ahead and cancel those because it's that much less typing that I got to do. And I've got a 0.6 times a 0.2. So let's whip out the calculator. And 0.6 times 0.2 should give us 0.12. And then that's times 10 to the 9. So this is basically 0.12 times 10 to the 9 newtons. If I want to move this over by 1, then I need to subtract 1 from the power. And so this force is, by the way, there's a negative sign here. It's going to be negative 1.2 times 10 to the 8th newtons. Now, with this said, some editions of the textbook actually seem to be giving the answer 1.0 times 10 to the 9 newtons, mutually repulsive. Well, of course, the mutually repulsive part is understandable because, again, they have plus 0.2, whereas I've got minus 0.2. So, you know, if you read carefully enough, then you know that that should be different. But other than that, there is this issue of the fact that they're off by basically an order of magnitude on theirs. So I tended to have a bit of leniency in grading this particular problem. In other words, while this one was the least easy problem, only 25.93% got this one right. It's sort of understandable given that the text gave you a wrong answer. And so if you just looked at the text's answer and didn't actually attempt the math, then that would explain why a number of people got it wrong. Of course, I'm also a little surprised that nobody actually emailed me to say, hey, could you check this answer? The text answer and my answer are different. I wasn't necessarily expecting a lot of such emails, but I'm kind of surprised that I didn't get any such emails. With that said, I was fairly lenient in grading this particular problem because one of the two editions of the text had the wrong answer. Here is one of the 3 questions that basically nobody was able to get right, or 4 questions that basically nobody was able to get right. So this one, 0% right. And I suppose that this question is a challenge for a certain type of learner. Again, not everybody actually got to attempt this question. There were only 6 attempts on it. So I should say of 6 tries. basically this one is in a sense a logical elimination type of question, but what you need in order to answer it is basically says you have one 6-socket power strip plugged into another 6-socket power strip, and then that's plugged into a wall socket. So we've got to figure out which of the statements are true. So let's just, for fun, sketch our wall socket. And that wall socket is plugged into strip number 1. Is plugged into strip 2. So here are the 6 socket outlets on number 2. This one then leads to strip number 1. And so we put in our 6 little guys here. And so this is 1, 2, and a wall. So our question is, which of these options best fits this diagram? In your notes, and specifically in the part of your notes on simple electric circuits and electrical safety, you have this diagram, and this corresponds to figure 8.11 in your text, which in my text is on page 213 because I'm using the 14th edition here. And what this is showing is you've got 3 appliances here, 1, 2, 3, and they're all in parallel with each other, on the same fuse or circuit breaker, or if you will, power strip. The reason why that is that if one of them burns out, you don't want everything to be burned out. So the little bit of logic that you have to use here is that a power strip works the same way. And you know that's true because you know that if a light bulb, let's say you plug 2 lamps into a power strip and you turn them both on, and one of them burns out, the other one can still keep running. Okay, so that means that your power strip must be wired the same way as this. So everything in your power strip needs to be in parallel. And then if you look here, you'll notice that basically this power strip or whatever is also in parallel with the stereo. Okay, so let's go back to our diagram. The rule again is if one thing burns out, so if one burns out, if all burn out, then they're in series. If no others burn out, then they are in parallel. Okay, so let's go back and see what we have happening here. So this one right here, we already established that, let's say you have a light bulb plugged in, like a lamp plugged in, you have a lamp plugged in, you got your phone charger plugged in. The lamp here burns out, well this lamp still runs, your phone charger still runs, etc. So that means that these are in parallel with each other. That also implies, incidentally, that these must be in parallel with each other. So we come up here and we eliminate anything that says that the sockets within a given power strip are in series with each other. So that gets rid of option A because that says that they're all in series with each other. Let's see here. All 6 on strip 2 are in series, so we can eliminate C. And the rest are parallels. Okay. Next thing. Suppose that you were to cause this guy to burn out in such a way that it's, equivalent to removing this wire. Okay, so if you remove this wire, that's equivalent to saying everything here burns out. What will happen to the light bulb here? Well, it will burn out. That means that this needs to be in series with this. So anything now that says that strip 1 is in parallel with strip 2 can be eliminated. So this right here says that all the all 6 sockets on each of these are in parallel with each other, and they're parallel with the wall socket. So we eliminate this one because it's saying that all of these are in parallel with all of these. These right here are series. This right here is series. Okay, all 6 are in parallel with each other. All 6 on power strip 1 parallel with each other, but power strip 1 is in series with power strip 2. Good. And that's in series with the wall. So that means that this one is correct. And since this is a select all which apply, so obviously if one's correct, then none of the above is not correct. So is this one correct? All 6 sockets on strip 2 are in parallel with each other. All 6 sockets on strip 1 are in parallel with each other. So far, so good. Power strip 1 is in series with the socket to which it is plugged in. So far, so good. Both are in parallel with the wall socket. Nope. So the answer would be D in this case. Last but not least on this post-quiz review, how many electrons per minute pass through a section of wire that has a resistance of 100 ohms and a voltage drop of 10 volts? Okay, there's a few things that are going on here. Basically, we need to, first of all, figure out what's the current. What is the current? And the current I is, as you recall, defined by the change in charge per unit time. So we know we're looking for a current because it's saying how many electrons this carries a charge. So charge carrier pass through a section of wire per minute. So this is per time. So we know we're looking for a current here. So how can we figure out this current? Well, as it turns out, we have Ohm's Law. So this was discussed in the notes, and it was discussed basically in section 8.2 of your text under current, voltage, and electrical power. So Ohm's law says that V equals IR, that is the voltage drop is the current times the resistance. Okay, so V is equal to I times R. That implies that I must be V over R. And so that implies that we have 10.0 volts per 100 ohms. And so this is 0.1 amps, which is the same thing as 0.1 coulombs per second. So let's convert this, convert current to electrons per minute. All right, well, 0.1 coulomb per second, we need to know how many electrons are in 1 coulomb. And we need to know how many seconds per minute. Well, this latter one is the easier one. I'm assuming you all know this. 60 seconds is 1 minute. So per minute, that would be 60 seconds per minute. And we want the thing to have per minute here. So where do we get this one from? Well, a number of you actually watched the examples that I did. Not very many of you, but a number of you did. And so you'll recall that I kept going back to this same old table 8.1 over and over and over again. So if you're just now joining us at this point, then, well, look it up in table 8.1. So 1 electron has a charge of 1.6 times 10 to the minus 19 coulombs. That's from table 8.1. So we'll just write that in here, table 8.1. So 1.60 times 10 to the minus 19 coulombs per 1 electron. So now we need to sort of put it all together. We basically have a current of 0.100 coulombs per second. We need to multiply that by 60 seconds per minute. So that's going to eliminate the seconds thing. Now we need to multiply by coulombs per electron. Electrons per coulomb. So 1 electron per 1.60 times 10 to the minus 19 coulombs. By the way, these electrons, usually the symbol we use is E minus. Okay, so out comes the calculator. We basically have 0.1 times 60 divided by 1.6. So that's 3.75, and then that's divided by 10 to the minus 19. So this right here should be 3.75 over 10 to the minus 19. This is E minus per minute. And of course, if you divide by 10 to some power, that's the same as multiplying by 10 to the negative of that power. So this is going to be 3.75 times 10 to the 19 electrons per minute. Okay, so that is all of the examples that I wanted to go through today, all of the quiz questions that I wanted to go through today. This one, by the way, to actually enter it correctly, you would need to go 3.75 E plus 19, or maybe just 3.75 E19, and that's what you would enter. So this is what you'd actually put into the answer box, and the unit of electrons per minute is sort of implied with that. So that's all of the quiz questions that I wanted to review today. Thanks for watching, and I hope you find this helpful in your further studies.